and shear stresses, right? So just we quickly in 10 minutes we quickly go through, then we will start understanding the other next chapter. So here we started with the assumption of, first we started with the bending theory, that is the bending stresses. We know the bending stresses is due to the bending moment. Stresses developed due to the bending moment, we call it as a bending stresses. So in the bending stresses, we assume as a pure bending. That means only bending will occur at a time, and shear will not consider that time for the calculation purpose, easy calculation purpose. That we call it as a pure bending, right? And no shear force occurs, only bending occurs. We call it as a pure bending. Next, assumptions are initially beams are straight, and cross section of a beam is cross section of beam is you can say is constant, and the beam is homogeneous material and is longitudinal plane of symmetry. Applied loads across the transverse section is zero, and the other members are this beam is failed by only bending, not the buckling. So I think last class we also discussed what is bending and what is buckling. So bending is nothing but when the beam is bending happens only, and the force applied along the perpendicular to the length of the member is called as bending, and the force acting along the length of the member we call it as a buckling, right? This is especially columns with the fails the beam is fails by buckling, and in the beams we fail by bending because the force is acts perpendicular to the length of the member, so that is called the bending. And the force is perpendicular. Next is buckling happens for the columns, nothing but axial load, that is the length is parallel to the force member, then the that such type of a member failing is known as a buckling, right? So that also will end, and also E will be the same for tension and compression, and the plane sections remains plane before bending, after bending we know this. The deformation of shear force is neglected in the bending, right? Then elastic limit is not exceed. So these are things, and mainly we understood the homogeneous material. What is the homogeneous material is, we understood the what is homogeneous material is. Homogeneous materials are defined as material of uniform composition throughout the section. So then we call it as a homogeneous. We take an example as apple. If you cut the apple, the taste everywhere is the same taste. So that we call it as a homogeneous material. Another example is will mix with the water with the salt, probably mixed. If you take the any sample there, the proportion anytime we take, the chemical composition is same everywhere throughout the this jar wherever the water is there. But the opposite of homogeneous is heterogeneous. That is nothing but the example is taken an oil plus water. If you mix how much time whatever you mix, but finally the oil will be take place at the top and water will be settled and down. So this is not a homogeneous material. We call it a heterogeneous material. This also we have learned last class, and here also just we discussed how the actual bending action will happen in a beams, right? So if a beam is bending, so if load is acting length perpendicular to the length of the member, as we just discussed, this is the perpendicular, this is the beam is here, and the load is acting perpendicular, that's why it is happens the bending. But if you wanted to the buckling, this beam should be the longitudinal and the force is like this will cause a buckling. Or the same beam, if you wanted buckling, it should be in this direction, force should be. But normally this no force will be acts in the beam in this direction, always the force will be act perpendicular to the beam. So that's why beam failure always has a bending failure, not the buckling. So what happened is bending is, while bending what happens is bottom fibers, if a simply supported beam, suppose the bottom fibers are in tension and top portion will be then compression. So if you see, notice here compression means the all the points are crushed each other, but the tension is upper because his length is increasing. But how the possible is length is increasing? Only possible when there is a cracks happen in the material, then only it will try to expand. So that's why please remember, whenever the beam is failure, it will start the cracking from the bottom, not from the top. If it is failures in tension, always the crack will start from the bottom and will it propagate to the top. So that's why if you see that, especially finally, as we also learn in the third years, the reinforcement always be provided in the tension zone, because this is the tension. So that's why in simply supported beam, reinforcement will provide at the bottom of the beam, not for the top, right? Because we know the concrete is also already strong in compression, so no need additional strength by providing the reinforcement at the top. Only we provide the reinforcement where the weak the portion of the concrete, that is at the bottom in the beam, simply supported beam. That's why we'll provide the reinforcement along the bottom of the length, right? That is simple logic. And the same thing if you case that cantilever beam, it will be what it will bend something like this, right? It will bend something like this. So in this case, tension will be the top, compression will be the bottom. So that time what we will do is we'll provide the reinforcement at the top portion of the beam, in the cantilever beam, right? So that you learn anyhow in the RCC design if you come this semester. So this is another topic we have learned already. So next already compression tension we have learned, and we okay. Okay. Next, we'll go for the next. We have discussed about the main bending formula is only one formula. We have to remember m by I is equal to f by y is equal to e by r. This is what is m, what is I clearly given, and we also will learn last class what is the bending stress. F is equal to bending stress. Y is equal to neutral axis from the neutral axis from to the extreme fiber, distance of the fiber from the neutral axis. That means where we are finding the bending stress from the neutral axis is nothing but the y. Only these two are little confused, and remaining I is moment of inertia of the whole section, m is equal to bending moment, e is equal to modulus of velocity, r is equal to radius of curvature. This way everybody knows. But please remember, while calculating the anything they ask in the question, you need to convert into the same one unit. All the forces or stresses in newtons per mm square or newton mm. All this convert into newtons and mms. Then your calculation may not do any mistake, right? So this also we learned. So they based on this, and the stress distribution in a bending stress always we see irrespective of the cross section, it is only the one shape. This is a triangular shape or linearly varying shape. I will consider as a linearly varying shape. All sections, if you see the triangular, rectangular, I section, anything, this will be the same proportions. It will be go the bending stress distribution. But only thing will differ is some based on the type of the beam, whether cantilever, simply supported, compression will be the top and tension will be to bottom. It may change sometimes. Top is tension and bottom is compression. But always the shape will be the same based on the given. Suppose this is given a simply supported beam, then the tension will be at the bottom and the compression will be at the top. Right? But it is linear variation only. Please remember, at the neutral axis it is zero. From this linearly changes. Circular shapes, everything is the same. So same thing we have already discussed last class. And also we have learned what is the moment of inertia and section modulus, what is the practically. So we limited. We another name of the moment of inertia is area moment of inertia. It is a measure the resistance to the bending about a certain axis. This call it as a moment of inertia, because we have more moment of inertia in that particular direction. Obviously, we will have more strength of this material. It's the same thing. If you see this beam is like this, moment of inertia is b d cube by 12, right? If d is less, so d cube 3 times, then we will get the moment of inertia less only, so that the beam will be easily will bend in this direction. But if you provide the same beam in this direction, B will be the small and the D will be the more. The moment of inertia of rectangular section, we know the formula BD by 12. So we will get the more resistance of the material. That's why if there is I is more, right? That's why we will measure the resistance or strength of a material by measuring the I. If any material have the I is more, you assume the bending resistance or strength is more, right? This is also discussed. Section modulus also we discussed. This is nothing but just I by y. So I by y we consider as a section modulus. This is also the sometimes instead of asking I, they will ask Z section modulus. It simply we find I and y. Y is nothing but neutral axis to the where we are finding the bending stress, that is known as y, right? So this is also the material section modulus also. So we have to remember some of the I sections or triangular sections, moment of inertia, what is the section modulus. So no need to remember section modulus, just remember the moment of inertia, then we divided by y, center of this one, then we will get the z simply. So, but moment of inertia, we need to remember I for rectangular section is BDQ by 12, and the triangular section BDQ by BHQ by 36, a circular section by D to the power of 4 by 64, something like this. And you need to remember the semicircle and all this stuff you need to already done the problem earlier classes, and you need to just remember the formulas. Okay, next we'll go on to the already discuss about the shear stresses. What is the difference between the bending stress and shear stress is the stress due the stresses due to the shear force will occur by shear stresses directly. The bending stress is due to the bending moment. Here the stress is due to shear force, we call it occurs the shear stresses. We know that shear force, what is the meaning of the shear force and bending moment? Bending moment is that will try to bend this beam into this is bending moment. Shear force always try to cut the section into two parts. The shear force, we see the member is like this. Shear force means it will perpendicular to this will try to cut the section, because in this direction it is very difficult to cut the section, only possible to cut the section in the smallest dimension. So that's why shear force always acts along the smallest part of the dimension of the member. So this is sometimes will be inclined also may happen. That is known as inclined shear force, horizontal shear force. So practical example is when just a knife we are cutting any ribbon, that will cut due to the shearing action. That is a shear force action. So here we can failure may be inclined as we discussed horizontal or sometimes vertical. So this portion suppose is horizontal failure, this is inclined, this is vertical shear force failure. So this is also we learned. And also we have learned the formula for the bend shear stress formula. This is nothing but the FA y bar by IB. So shear stress is equal to represented by Q and bending stress is equal to small f. So here is the shear stress Q, F into A into y bar by IB. This formula we already discussed last class. But here only is important is what is A and what is Y and what is B. These three parameters, many of students will do mistakes in the problem. Those things you need to be remember. Q is A is nothing but, again I'm repeating, A is nothing but area of the cross section where we need to find the shear stress from the nearest extreme fiber. What does that mean? Suppose there is a section. Suppose there is a section here. This is the cross section. So I need to find the shear stress at the top. Then what will be the area? Area is nothing but neutral axis to the, sorry, what is area is where you are finding the shear stress to the nearest extreme fiber. So since we are taking at the top only, the nearest also the top, then area will be the 0. Suppose you are taking at the neutral axis, the middle of the cross section as the shearing stress, then the what will be the area of the section is nothing but the line from the where you are finding the shear stress to the nearest extreme fiber. That means either upper or bottom. Since it is the center, it is both sides are equal, so that's why you can take either top or bottom. Both are same. So that portion we call it as the area of the section, shear center to the top of the fiber or bottom of the. Suppose you are taken in between the middle and the somewhere top part, then the area of section will be the where you are taking the stress from the nearest is the top fiber. So this small area we call to the area of the section. So here y bar is nothing but, please remember, y bar is nothing but area of centroidal area of the section shaded area where you are finding A, from that centroid to the neutral axis we consider as a y bar. And B is the where you are finding the shear stress, that is known as a B. So this what we have discussed last class. And also we have learned the material of isotropic. What is the meaning of isotropic? Isotropic is nothing but the material having the same property in all the three directions of a dimensions we consider as isotropic, right? But if you see that when all the metals and glasses are isotropic, but wood is not isotropic material, because if you see the strips are happen, if you take the one part of the strip with the point, you can one property will get, suppose that same if you consider backside, you will get the different value of that value of the property, because this we know this the wood will be formed by means of the strips, right? So they have different strengths at different points. So that's why we'll not consider as a wood as a isotropic material, but we consider all the steel and whatever the glass we consider as isotropic material, right? So these are the isotropic also we have learned. And also I'll learn, this is important topic we learned, is complementary shear. Complementary shear means what is nothing complementary shear? As we know, shear force always acts where in which direction shear force is acting, right? So suppose in this direction, first case, if you see here, the beam is horizontal, force is acting vertical. That means normally people will see the shear force also, stress also acts in the perpendicular direction. That is vertical shear stress. But sometimes what happens, suppose the material, there are two materials are placed one above the other, and then there is a force of vertical shear force acting. So for this case, or vertical shear force also acts, but along with this, because these strips will try to move over each other, due to that there will be the horizontal shear force also acts, that will be shear stress also acts, that will be considered as the complementary, that is additional. Only instead of vertical force, vertical shear stress acting, in addition we are getting horizontal shear stress also. That's why we call it as a complementary shear. That is nothing but the complementary shear. So next also we have learned, when there is a force is acting along the length of the angle is 0, then we call it as a shear force will act. Shear is nothing but the just shear of the section. That means cut the section in two parts, we call it as shear force. But the force is acting perpendicular to the cross section, then will be considered as a normal stress. Also considered as a bending stress. Both is the same. Don't confuse normal stress or bending stress or flexural stress. Both are the same meaning. Shear stress is different, but bending stress, normal stress, or flexural stress, both are same. I think, but the same. Flexure means or bending, flexure, or normal is the same, right? So when the angle is 90 degrees, you will get the bending stress or normal stress. The angle is 0 degrees, shear stress, and the angle is 45 degrees, we will get both shear stress and normal stress, because inclined forces will resolve it into horizontal as well as a vertical, right? This is an, sometimes they may ask in the gate this type of questions as well. And the force is acting in a other than the 0 degrees, if the 0 degrees is the shear stress will happen, and if the angle is 90 degrees to the cross section, we will get the bending stress, and if the angle is in between, we will get the both shear and uh, normal stress or bending stress, right? This is also we learned. Also, we have checked one practical problems how we can able to find the shear stress. So suppose here in this example we have checked shear stress at neutral axis. That means neutral axis there we need to find the shear stress. So in this case, what will be the A? A will be, as we discussed, area is always where we need to find the shear stress to the nearest extreme fiber. Here we are considering the center. So either you can take top or bottom is the same. So this is the cross sectional area we need to take, right? So that is the A will come, and Y will be nothing but a shaded area centroid from the neutral axis is nothing but the Y. And B is this beam. So you can able to do this. So this is the just thing. And next, suppose in this problem they ask to find the shear stress at the section AA. But if you see the AA is given here, so area will be from that point to the nearest extreme fiber is top. So this will be the shaded area. You should not able to consider bottom in the extreme fiber, because this is the more area. This is not the nearest. This extreme fiber is longer and this is the shortest. So that's why we consider the shortest extreme fiber area. And this centroid Y bar is nothing but the centroid of the shaded area from the neutral axis is Y bar. So now I think you may understood and what is the concept of this thing. And if you see the shear stress distribution, how it will be happen is the zero at the extreme fiber, both extreme fibers. As we know, because A is becoming zero here, because A is nothing but where you are finding the shear stress to the nearest extreme fiber. Suppose you are finding the shear stress here, always the extreme fiber is zero, so A is zero. Suppose here also if you see this force, nearest extreme fiber is this, so it is zero. That's why these values are becoming zero, but always maximum at the neutral axis. If you see everywhere, neutral axis maximum and extreme fiber is zero. So same thing, if you give any shape of this cross section, you will find the extreme fiber is zero and your neutral axis is maximum. All right. So this you have to remember. So sometimes they will give the shape of the diagram, and you need to be mark the what is the given shape, the shear stress distribution shape, right? So this anyhow I will share you later. But these things we have discussed in the last class, and maybe we'll continue this little bit problem start here. So here just is one more topic is shear flow. Sometimes in the gate they're asking the shear flow, how they will give some shape and how they will give multiple choice A, B, C, D, and you need to find what is the correct shear flow. So for that there is one logic is there. So please remember, whenever the shear flow diagram is given, you need to mark the shear flow. I think, but how the shear stress will distribute, that is the meaning by the shear flow. So there is a logic you have to remember. Always remember, shear flow tends to maximum at neutral axis. So wherever the maximum of the section will get the neutral axis, will get the maximum shear force, shear flow, and the zero at the free edge. If you find any point free end, there we'll find the zero shear flow. This is the main logic. You can able to identify the problems by using these 2 points. Maximum at the neutral axis and the zero at the free end. Please remember, the free end means for the I section, free end will be these two, and the top and bottom. Please remember, this is the free ends, right? But any other portion is not called as a free end, right? Only the edges, extreme edges we consider as the free end. So all the extreme edges, the shear flow will be the zero. If you consider here, if you see extreme edge here, so that's why this will be shear flow is considered as zero. And here also triangle is zero, here also zero. If you see this figure, it is zero, it is zero, it is zero. Here also if you see, it is zero, it is zero, it is zero, right? So if you see the next I section, here I section, what is the shear flows will be is the only, this is the free edge. I section only these two are the free edges. That's why you can see this is the only zero at the shear stress. Remaining is dot zeros, right? If you can see this thing, or you can able to see from this portion, or you can see this, or this is also the free edge. That's why you can getting the zero at the free edge. But the T section, if you see, T section only free end is zero, and this is zero. That's why it is zero. It is zero. and here also it is 0. See, this is also free edge, so that's why the shape will be like this. So this we will do one for two problems, we can able to know, but for a fun of concept remembering, please remember shear flow always, shear flow diagram at the extreme edges is 0, free edge is 0, and the maximum at the neutral axis. Just remember these 2 points, then we will do this. Okay, so these are the